Earth spins through the void, tracing its familiar ellipse around the Sun with what appears to be clockwork precision. For most purposes, this orbital dance remains predictable. Sunrise follows sunset. Seasons cycle with gentle reliability, and the planet maintains its steady 93 million mile average distance from our star. Yet beneath this apparent order lies a web of gravitational whispers so complex that even the most sophisticated computers cannot fully capture Earth's orbital future. The illusion of orbital simplicity begins with the Sun's overwhelming gravitational dominance. Our star contains 99.86% of the solar system's mass, creating a gravitational well so deep the Earth cannot escape its pull. This central force follows Newton's inverse square law with mathematical elegance. Twice the distance means 1/4 the gravitational pull. The relationship appears simple, almost elegant in its straightforward geometry. The Earth-Sun system, considered in isolation, produces orbital predictions of stunning accuracy extending millions of years into the future. Only when other bodies enter the calculation does the mathematics begin to fracture into something far more intricate. The solar system contains not just Earth and Sun, but 8 planets, over 200 moons, millions of asteroids, billions of comets, and countless particles of interplanetary dust. Each object, no matter how small, exerts its own gravitational influence on every other object. The cumulative effect creates what mathematicians call the n-body problem, a system of gravitational interactions so complex that no analytical solution exists. Jupiter lurks in the outer solar system, its massive presence creating subtle perturbations that ripple inward toward Earth's orbit. Though separated by hundreds of millions of miles, the gas giant's gravitational field reaches across space with invisible fingers, gently tugging at Earth's trajectory in ways that compound over geological time. These influences measure mere millimeters per year, yet they accumulate across millennia into measurable orbital shifts. Jupiter's orbital period of nearly 12 Earth years creates a gravitational rhythm that pulses through the inner solar system, sometimes reinforcing Earth's orbital characteristics and sometimes opposing them. The mystery deepens when scientists attempt to predict Earth's precise position centuries into the future. Each gravitational calculation requires knowledge of every other body's location, velocity, and mass, creating an interconnected web where uncertainty in one element propagates through the entire system. A small error in measuring Jupiter's position today becomes a larger error in Earth's predicted location tomorrow, and an exponentially larger error in its position next century. This sensitive dependence on initial conditions transforms minor measurement uncertainties into major predictive limitations. Venus and Mercury add their own gravitational voices to the cosmic chorus. Venus, Earth's nearest planetary neighbour, completes its orbit in 225 Earth days, creating a complex pattern of gravitational alignment and opposition that repeats every 584 days. Mercury races around the Sun in just 88 days, its rapid orbital motion creating high-frequency gravitational perturbations that affect Earth's trajectory in subtle but measurable ways. The 3 inner planets engage in an intricate gravitational dance where each participant influences the others in an endless feedback loop. Even more quietly, the Moon drifts away from Earth at roughly the same rate that fingernails grow, a seemingly trivial 3.8 centimeters per year. This gradual recession alters the Earth-Moon gravitational relationship, subtly modifying our planet's orbital characteristics in ways that unfold over millions of years. The lunar influence that once held Earth's orbit in one configuration slowly weakens, allowing other gravitational voices to speak more loudly in the cosmic conversation. Early in Earth's history, when the Moon orbited much closer, Its gravitational influence dominated the planet's orbital evolution. As the Moon retreats, that dominance gradually shifts toward the more distant but massive planets. The Sun itself proves less constant than ancient astronomers assumed. Solar mass decreases by approximately 4.3 million tons per second as nuclear fusion converts matter into energy. This mass loss, though infinitesimal compared to the Sun's total mass, gradually weakens the gravitational force that holds Earth in orbit. The effect allows Earth's orbital radius to expand by about 1.5 centimeters per year, a gentle spiral outward that unfolds over billions of years. The irony emerges slowly. The same fusion process that sustains life on Earth also weakens the gravitational bond that keeps our planet in its life-supporting orbit. Beyond the classical gravitational influences lies the subtle realm of relativistic effects. Einstein's general relativity reveals that massive objects warp the fabric of space-time itself, creating gravitational fields that differ slightly from Newton's predictions. Mercury's orbit precesses by an extra 43 arc-seconds per century due to these relativistic corrections, a tiny deviation that becomes significant when projected across cosmic timescales. Earth experiences similar but smaller relativistic effects that introduce additional uncertainty into long-term orbital calculations. Modern astronomers face the humbling reality that orbital prediction becomes increasingly uncertain as time horizons extend. They can calculate Earth's position next week with extraordinary precision, measuring its location to within centimeters. Next month brings slightly larger uncertainties. Next year introduces meter-scale margins of error, and next century expands those uncertainties to thousands of kilometers. The mathematics of gravitational interaction preserves detailed information about orbital positions for limited time periods before chaos theory takes over and prediction dissolves into statistical probability. The quest for orbital precision reveals a deeper truth about the universe, that even the most fundamental physical processes contain elements of irreducible uncertainty. Earth's orbit appears stable and predictable on human timescales, yet extends into a future where countless gravitational influences will slowly but inevitably alter its path through space. Only the present moment offers true certainty in the gravitational dance that carries our world through the cosmos. The Moon drifts silently away from Earth, its ancient face growing smaller with each passing century, in a recession so gradual that human lifetimes cannot perceive its motion. This lunar retreat unfolds at the glacial pace of continental drift, 3.8 centimeter per year, roughly the speed at which human fingernails grow, yet this seemingly insignificant distance accumulates across geological time into a transformation that fundamentally alters Earth's orbital characteristics and rotational behavior. 4.5 billion years ago, when Earth's surface still glowed with molten rock and the atmosphere consisted of volcanic gases, the Moon orbited much closer to our planet. Recent lunar samples and computer simulations suggest that Luna once hung in Earth's sky at a distance of perhaps 22,000 kilometers, close enough that it would have appeared 14 times larger than today's Moon and created tides hundreds of meters high. The gravitational forces between Earth and its satellite were correspondingly more intense, locking the two bodies in a tighter orbital embrace that has been slowly unwinding ever since. Tidal friction drives this gradual separation through a process as elegant as it is inexorable. Earth's rotation carries its tidal bulges slightly ahead of the Moon's position, creating a gravitational torque that transfers angular momentum from Earth's spin to Luna's orbital motion. The planet loses rotational energy and slows down, while the Moon gains orbital energy and spirals outward. This energy exchange operates with the patience of geological time, requiring millions of years to produce measurable changes in the Earth-Moon system. The mathematics of tidal recession reveal why the Moon's influence on Earth's orbital prediction becomes increasingly subtle. As Luna moves away, its gravitational effect on Earth weakens according to the inverse square law. Twice the distance produces 1/4 the gravitational influence. The Moon that once dominated Earth's orbital evolution through its powerful nearby presence gradually yields that dominance to the more distant but far more massive planets. Jupiter's gravitational perturbations, once overwhelmed by lunar effects, begin to assert themselves more strongly in Earth's orbital dynamics. Evidence of the Moon's ancient proximity persists in Earth's geological record through fossilized tidal rhythmites, sedimentary layers deposited by ancient tides that recorded the lunar month and Earth's day length across deep time. These stone archives reveal that 620 million years ago, when primitive multicellular life was just beginning to experiment with complex forms, the Moon orbited closer to Earth, and a day lasted only 21.9 hours. The lunar month consisted of just 20 days, creating a calendar utterly foreign to modern experience. Earth spun faster, the Moon loomed larger, and tidal forces sculpted coastlines with far greater intensity than today's gentle oceanic rhythms. The Moon's recession carries profound implications for Earth's long-term orbital stability. Luna's gravitational influence helps stabilize Earth's axial tilt, preventing the chaotic tumbling that might otherwise result from planetary perturbations. Mars, lacking a large stabilizing satellite, experiences axial variations that swing its poles through angles of 60 degrees or more over millions of years. Earth's 23.5-degree tilt remains relatively stable, oscillating only between 22.1 and 24.5 degrees over 41,000-year cycles, largely because the Moon's gravity acts as a cosmic gyroscope that resists changes to our planet's rotational axis. As the Moon continues its outward spiral, this stabilizing influence will gradually weaken. Computer models suggest that in approximately 2 billion years, when the Sun has grown significantly brighter and Earth's oceans have begun to evaporate, the Moon will orbit at roughly 1.6 times its current distance. At that remote epoch, Earth's axial stability will depend more heavily on the gravitational influences of Jupiter and the other giant planets, potentially allowing larger variations in obliquity that could dramatically alter the planet's climate patterns. The recession process itself contains a built-in limit that will eventually halt the Moon's outward journey. Tidal friction not only moves the Moon away from Earth, but also slows our planet's rotation until the day length matches the lunar orbital period. This process, called tidal locking, will eventually synchronize Earth's rotation with the Moon's orbit, creating a situation where the same hemisphere of Earth always faces Luna. When this tidal equilibrium is reached in approximately 50 billion years, long after the Sun has evolved beyond its current state, the Moon will stop receding and begin a slow return journey toward Earth. The irony of lunar recession extends beyond its effects on Earth's orbital dynamics to encompass the very observations that reveal the process. Ancient eclipse records from Babylon, China, and medieval Europe provide precise timing data that allow astronomers to calculate how Earth's rotation has slowed over the past several millennia. Solar eclipses that historical records describe as total would appear partial today because the Moon has moved slightly farther away, reducing its apparent size in Earth's sky. These subtle differences between predicted and observed eclipse paths reveal the Moon's recession with extraordinary precision. Modern laser ranging experiments confirm the Moon's retreat through measurements of stunning accuracy. Since 1969, when Apollo astronauts placed retroreflectors on the lunar surface, Scientists have bounced laser beams off these mirrors to measure the Earth-Moon distance with millimeter precision. These experiments not only verify the 8 centimeter annual recession, but also reveal smaller variations in the process caused by Earth's changing rotation rate and the complex dynamics of the Earth-Moon-Sun system. The Moon's gradual departure introduces subtle but measurable uncertainties into Earth's orbital predictions. As Luna's gravitational influence weakens, Earth becomes more susceptible to perturbations from the planets, particularly Venus and Mars during their closest approaches. The changing Earth-Moon center of mass, called the barycenter, shifts Earth's orbital path in ways that compound over centuries into significant positional uncertainties. What appears as a simple two-body problem today slowly transforms into a more complex gravitational environment, where planetary influences assert themselves with increasing authority. Contemporary lunar recession may be accelerating due to changes in Earth's ocean basins and tidal dissipation patterns. The formation and melting of ice sheets during glacial cycles alters the planet's moment of inertia, affecting its rotation rate and the efficiency of tidal energy transfer. Human activities that modify coastal geography and ocean depths may also influence tidal dissipation, though these effects remain too small to measure with current instruments. The Moon's future recession rate depends on Earth's evolving geophysical characteristics in ways that introduce additional uncertainty into long-term orbital calculations. The story of lunar recession unfolds as a meditation on cosmic patience and the accumulation of infinitesimal changes across vast timescales. Each night, the Moon moves imperceptibly farther from Earth, its gravitational grip weakening by amounts too small for human perception. Yet over the millions of nights that constitute geological time, these minute changes reshape the gravitational architecture of the Earth-Moon system and alter our planet's orbital behavior in ways that even the most sophisticated computer models struggle to predict with perfect accuracy. Jupiter hangs in the outer darkness beyond Mars, a gas giant so massive that it contains more matter than all other planets combined, yet orbits the Sun at a distance where its gravitational influence on Earth seems almost negligible. 500 million miles of space separate the giant planet from our world, a gulf so vast that light takes nearly 3/4 of an hour to cross it. Yet across this cosmic void, Jupiter's immense gravitational field reaches toward Earth with invisible persistence, creating subtle orbital perturbations that accumulate over millennia into significant deviations from predicted paths. The scale of Jupiter's mass defies easy comprehension, with 318 times Earth's mass compressed into its swirling atmosphere and metallic hydrogen core. Jupiter warps space-time around itself in ways that affect every object in the solar system. The planet's gravitational field is so powerful that it captures asteroids into complex orbital resonances, shepherds the asteroid belt into its current configuration, and deflects incoming comets in trajectories that sometimes send them careening toward the inner planets or fling them entirely out of the solar system. This gravitational influence operates through mechanisms both direct and indirect, creating a web of perturbations that complicate Earth's orbital predictions in ways that emerge slowly over extended time periods. Jupiter's 11.86-year orbital period creates a gravitational rhythm that pulses through the inner solar system, sometimes reinforcing Earth's orbital characteristics and sometimes opposing them. When Jupiter and Earth align on the same side of the Sun, their combined gravitational pull subtly affects the entire solar system's center of mass, creating perturbations that ripple through planetary orbits for decades. The mathematics of Jupiter's influence involve what astronomers call secular perturbations, long-term changes in orbital elements that unfold over thousands or millions of years rather than the short-term variations visible from year to year. These secular effects alter Earth's orbital eccentricity, the shape parameter that describes how elliptical rather than circular our planet's path appears, over roughly 100,000-year cycles. Jupiter's gravitational influence causes Earth's orbital eccentricity to vary between 0.000055 and 0.0679, transforming our planet's path from nearly circular to noticeably elliptical and back again. The irony of Jupiter's influence lies in its dual nature as both stabilizer and perturber of inner planet orbits. Computer simulations suggest that without Jupiter's massive presence, Earth's orbit would be far less stable over geological timescales. The gas giant acts as a gravitational shield, deflecting many asteroids and comets away from the inner solar system before they can impact Earth or the other terrestrial planets. Yet this same protective influence creates the orbital perturbations that make Earth's precise future position impossible to predict beyond certain time horizons. Recent research reveals that Jupiter's orbit itself undergoes slow changes that affect its gravitational influence on Earth in complex ways. The giant planet participates in gravitational resonances with Saturn that cause both planets' orbits to evolve over millions of years. These slow orbital changes alter the strength and timing of Jupiter's perturbations on Earth's orbit, introducing additional layers of uncertainty into long-term predictions. What appears as a stable gravitational influence today slowly shifts in ways that compound the difficulty of orbital forecasting. The Nice model of solar system evolution suggests that Jupiter and the other giant planets migrated inward and then outward during the solar system's first billion years, fundamentally restructuring the architecture of planetary orbits. Evidence for this migration appears in the current orbital configuration of the outer planets and the distribution of objects in the Kuiper belt beyond Neptune. If such large-scale orbital migration occurred in the past, it raises questions about the long-term stability of current planetary positions and the possibility of future orbital evolution driven by gravitational interactions among the giant planets. Jupiter's gravitational field creates resonance effects that demonstrate how small periodic forces can produce large cumulative changes over extended time periods. The Kirkwood gaps in the asteroid belt mark orbital distances where asteroids experience gravitational resonances with Jupiter, locations where the asteroid orbital period forms simple ratios like 3, 1 or 2, 1 with Jupiter's 12-year orbit. At these resonance locations, Jupiter's repeated gravitational tugs occur at the same point in the asteroid's orbit, gradually building up perturbations that eventually eject the asteroid from its original path. Earth experiences similar but much weaker resonance effects from Jupiter's gravitational field. These resonances operate over much longer timescales than the asteroid belt interactions, requiring millions of years to produce measurable orbital changes. The complexity arises because Earth simultaneously experiences resonance effects from multiple planets, not just Jupiter but also Venus, Mars, and the other giant planets, creating overlapping patterns of gravitational influence that interact in ways too complex for analytical solutions. Modern computational methods reveal the chaotic nature of Jupiter's long-term gravitational influence on Earth's orbit. Small uncertainties in Jupiter's current position and velocity propagate through gravitational calculations to create exponentially growing uncertainties in Earth's predicted future orbit. This sensitive dependence on initial conditions means that tiny measurement errors in Jupiter's orbital parameters today translate into enormous uncertainties in Earth's orbital position millions of years from now. The challenge of predicting Jupiter's own orbital evolution compounds the difficulty of forecasting its influence on Earth. The gas giant participates in a complex gravitational dance with Saturn, Uranus, and Neptune that creates chaotic dynamics in the outer solar system. These interactions unfold over time, scales of millions to hundreds of millions of years, making Jupiter's future orbital parameters uncertain and therefore making its future influence on Earth impossible to calculate with perfect precision. Observational evidence for Jupiter's perturbations of Earth's orbit appears in subtle variations in our planet's distance from the Sun and the timing of seasonal changes. No, these variations, measured through precise astronomical observations and analysis of paleoclimatic records, reveal the fingerprint of Jupiter's gravitational influence operating across geological timescales. Ice core data and sedimentary records preserve evidence of climate cycles that correlate with calculated periods of Jovian orbital influence, providing empirical confirmation of the gas giant's role in Earth's long-term orbital evolution. The study of Jupiter's gravitational effects on Earth illuminates a fundamental tension in orbital mechanics between apparent stability and underlying chaos. Earth's orbit remains stable enough to maintain relatively constant climatic conditions over geological time, yet sensitive enough to Jupiter's distant influence that long-term orbital prediction becomes impossible. This paradox reflects the nature of gravitational systems where apparently stable configurations contain seeds of unpredictability that emerge only when viewed across sufficiently extended time horizons. Jupiter continues its stately progress around the Sun, its massive presence creating gravitational currents that flow through the solar system with patient persistence. Each orbit of the giant planet shifts the gravitational landscape slightly, altering the subtle forces that guide Earth's path through space in ways too small for immediate detection but large enough to accumulate across cosmic time into orbital changes that reshape our planet's relationship with the Sun. The Sun breathes across space in a continuous exhalation of charged particles and electromagnetic radiation, creating what scientists call the solar wind, a stream of protons and electrons that flows outward from our star at speeds exceeding 1 million miles per hour. This invisible river of solar matter carries with it magnetic field lines that stretch across the solar system, creating a dynamic environment where electromagnetic forces interact with gravitational dynamics in ways that subtly influence planetary orbits over extended time periods. Solar wind particles strike Earth's magnetosphere with pressures measured in mere billionths of atmospheric pressure at sea level. Yet these seemingly negligible forces accumulate over geological time into measurable orbital effects. The magnetosphere, Earth's protective magnetic bubble, deflects most solar wind particles around the planet, but the interaction creates a bow shock wave that experiences constant pressure from the flowing solar plasma. This pressure varies with solar activity cycles, creating oscillating forces that push against Earth's magnetic field and subtly affect the planet's orbital velocity. Radiation pressure from sunlight itself contributes additional forces that perturb Earth's orbital motion in ways too small for casual detection, but significant enough to appear in precision, astronomical calculations. Each photon of sunlight carries momentum that transfers to any object it strikes, creating a gentle but persistent push away from the Sun. For Earth, with its massive bulk and relatively small cross-sectional area, radiation pressure effects remain minimal, yet over millions of years, even these minute forces contribute to the cumulative uncertainty that makes long-term orbital prediction impossible. The solar wind exhibits dramatic variations that correlate with the Sun's magnetic activity cycles, most prominently the 11-year sunspot cycle that alternates between solar maximum and minimum conditions. During solar maximum, when the Sun's magnetic field becomes highly twisted and unstable, solar wind intensity can increase by factors of 10 or more above quiet conditions. Coronal mass ejections, massive eruptions of solar plasma, can accelerate billions of tons of charged particles to speeds approaching 3 million miles per hour, creating shock waves that propagate throughout the solar system. These variations in solar wind intensity create corresponding changes in the electromagnetic forces acting on Earth and other planets. During periods of high solar activity, increased radiation pressure and particle bombardment create slightly stronger forces that tend to push planets away from the Sun. During solar minimum conditions, when the solar wind weakens to its quietest levels, these outward forces diminish correspondingly. The net effect introduces small but measurable variations in planetary orbital velocities that compound over centuries into significant uncertainties in orbital position calculations. Historical records of solar activity, preserved in ice cores, tree rings, and other paleoclimatic archives, reveal that the Sun's electromagnetic output has varied significantly over time, scales ranging from years to millennia. The Maunder minimum, a period of reduced solar activity between 1645 and 1715, coincided with unusually cold temperatures across Europe and North America, demonstrating the Sun's variable influence on Earth's climate system. Less obvious but equally real are the orbital perturbations that such long-term solar variations create through their effects on radiation pressure and electromagnetic forces. The interaction between solar wind and planetary magnetospheres creates additional complications for orbital prediction through processes that couple electromagnetic and gravitational effects in complex ways. Earth's magnetic field channels some solar wind particles into the polar regions, where they create aurora displays and deposit energy into the upper atmosphere. This energy deposition affects atmospheric density at satellite altitudes, creating drag forces that slowly alter the orbits of artificial satellites and contribute to atmospheric escape processes that gradually reduce Earth's mass. Atmospheric escape, driven partly by solar wind interactions with Earth's upper atmosphere, removes approximately 3 kilograms of atmospheric mass per second from our planet. This mass loss, though infinitesimal compared to Earth's total mass, gradually reduces the gravitational forces in the Earth-Moon system and affects long-term orbital evolution. The rate of atmospheric escape depends on solar activity levels, creating another link between solar variability and orbital dynamics that unfolds over geological timescales. The solar wind carries with it the Sun's magnetic field in a configuration called the interplanetary magnetic field, which extends throughout the solar system and influences the motion of charged particles around all the planets. This magnetic field undergoes reversals and reconfigurations that correlate with solar activity cycles, creating time-varying electromagnetic environments that affect satellite orbits and potentially influence long-term planetary orbital evolution through subtle electromagnetic forces. Precision measurements of solar wind properties reveal additional complexities that contribute to orbital prediction difficulties. The solar wind exhibits turbulence, shock waves, and magnetic field discontinuities that create irregular variations in the forces acting on planetary magnetospheres. These irregularities occur on timescales ranging from minutes to years, creating a spectrum of perturbations that interact with orbital mechanics in ways too complex for complete theoretical modeling. The heliosphere, the vast bubble of solar wind that surrounds the entire solar system, creates a boundary condition that affects the gravitational environment through its interaction with interstellar space. The heliopause, where solar wind meets the interstellar medium, lies roughly 120 astronomical units from the Sun, far beyond the orbits of all known planets. Yet this boundary influences the distribution of cosmic rays and interstellar particles that enter the solar system, creating subtle variations in the local gravitational environment that may affect long-term orbital stability. Recent space missions, including the Voyager probes and the Parker Solar Probe, reveal that the solar wind environment exhibits far more complexity and variability than early theoretical models suggested. The solar wind speed, density, temperature, and magnetic field strength all vary continuously, creating a dynamic electromagnetic environment that influences planetary orbits through mechanisms still being discovered and quantified by solar physicists and orbital dynamicists. The solar wind's influence on orbital prediction extends beyond direct electromagnetic forces to include its effects on space debris and micrometeorite populations that create additional perturbations on planetary motion. Solar wind pressure affects the orbits of small particles throughout the solar system, altering the distribution of dust and debris that planets encounter in their orbital paths. These encounters, while individually insignificant, accumulate over geological time into measurable changes in planetary masses and orbital characteristics. Solar storms, intense bursts of solar wind and electromagnetic radiation, can temporarily overwhelm planetary magnetospheres and create dramatic increases in the electromagnetic forces acting on orbital bodies. The largest recorded solar storm. The Carrington event of 1859 created aurora displays visible as far south as the Caribbean and induced electrical currents strong enough to disrupt telegraph systems worldwide. Such events, occurring perhaps once per century on average, create temporary but significant perturbations in the electromagnetic environment that affects orbital dynamics. The challenge of incorporating solar wind effects into orbital predictions reflects the broader difficulty of coupling electromagnetic and gravitational physics across the vast range of time and distance scales relevant to planetary motion. Solar wind variations occur on timescales of minutes to decades, while their cumulative orbital effects unfold over centuries to millennia. This separation of timescales makes it difficult to connect observed solar variability with measured changes in planetary orbits. Yet the connection undoubtedly exists and contributes to the fundamental unpredictability of long-term orbital evolution. Modern computational models attempt to include solar wind effects in orbital calculations, but the complexity of the coupled electromagnetic gravitational system requires approximations and simplifications that introduce additional uncertainties into predictions. The solar wind environment itself remains partially unpredictable, particularly during periods of high solar activity when the sun's magnetic field undergoes rapid and chaotic changes that affect solar wind properties in ways too complex for complete theoretical modelling. The sun continues its steady nuclear burning, converting 4 million tons of matter into energy each second, while simultaneously exhaling the solar wind that carries solar material throughout the planetary system. This dual process, energy generation and mass loss, creates the electromagnetic environment in which Earth's orbital motion unfolds, adding layers of complexity to gravitational dynamics that ensure the impossibility of perfect long-term orbital prediction, even as they maintain the broader stability that allows life to persist on our slowly wandering world. Between Mars and Jupiter lies a vast region of space populated by millions of rocky fragments, the asteroid belt, a cosmic debris field that stretches across nearly 200 million miles of the solar system's middle distance. These remnants of planetary formation, ranging in size from grain-sized particles to objects hundreds of kilometers across, create a complex gravitational environment where resonance effects and orbital interactions contribute subtle but persistent perturbations to Earth's orbital motion over geological timescales. The asteroid belt contains perhaps 2 million objects larger than 1 kilometer in diameter, with a total mass roughly equivalent to 4% of Earth's moon. This distributed mass creates gravitational influences that, while individually negligible, collectively contribute to the complex web of forces that make precise long-term orbital prediction impossible. Each asteroid follows its own elliptical path around the Sun, and the combined gravitational effects of these millions of orbiting bodies create small perturbations that ripple through the inner solar system. Ceres, the largest asteroid and the only dwarf planet in the asteroid belt, contains approximately 1/3 of the belt's total mass within its 940-kilometer diameter. This substantial concentration of matter creates gravitational effects measurable enough to appear in precision calculations of planetary motion. Ceres completes its orbit around the Sun every 6 Earth years, creating a gravitational rhythm that subtly influences the orbits of nearby asteroids and contributes to the long-term perturbations that affect Earth's orbital evolution. The distribution of asteroids throughout the belt follows patterns shaped by gravitational resonances with Jupiter, creating a complex structure of gaps and concentrations that astronomers call Kirkwood gaps. These gaps occur at orbital distances where asteroid periods form simple mathematical ratios with Jupiter's 11.86-year orbit, locations where the gas giant's repeated gravitational tugs gradually remove asteroids over millions of years. The resulting structure creates a non-uniform gravitational field that varies with position and contributes to the irregular perturbations experienced by objects passing through or near the asteroid belt region. Asteroid families, groups of objects that share similar orbital characteristics and likely originated from the collision and fragmentation of larger parent bodies, create clusters of gravitational influence that change the local gravitational environment in ways that affect long-term orbital stability. The Flora family, containing over 13,000 known asteroids in the inner belt, creates a concentration of gravitational influence that affects the motion of Mars and contributes indirectly to Earth's orbital perturbations through the complex chain of gravitational interactions that connects all solar system bodies. The Trojan asteroids, captured in Jupiter's gravitational influence at the stable Lagrange points that lead and follow the giant planet in its orbit, create additional gravitational concentrations that affect the outer solar system's dynamics. These asteroid populations, numbering in the hundreds of thousands, orbit in gravitational harmony with Jupiter while creating small but measurable perturbations that influence the orbital evolution of the gas giant itself and thereby affect Jupiter's long-term influence on Earth's orbital motion. Recent discoveries reveal that asteroid orbits exhibit chaotic behavior over million-year timescales, with small gravitational perturbations from planets causing some asteroids to migrate between different regions of the solar system. These orbital migrations alter the mass distribution within the asteroid belt and change the gravitational influences acting on planetary orbits in ways that contribute to the unpredictability of long-term orbital evolution. Computer simulations suggest that roughly 20% of asteroids will experience significant orbital changes over 100 million-year periods. The Yarkovsky effect, a subtle force created when rotating asteroids absorb sunlight and re-radiate thermal energy, causes gradual orbital evolution for smaller asteroid belt objects that indirectly affects the gravitational environment experienced by larger bodies. This thermal force, operating over millions of years, can migrate asteroids across significant orbital distances and alter the mass distribution within the belt in ways that change the collective gravitational influence of asteroid populations on planetary motion. Near-Earth asteroids, objects whose orbits bring them close to Earth's path around the Sun, create more direct gravitational influences that contribute to orbital prediction uncertainties. These objects, numbering in the tens of thousands, periodically approach Earth at distances close enough that their gravitational effects become temporarily significant. During close approaches, even relatively small asteroids can create measurable perturbations in Earth's orbital velocity that contribute to the cumulative uncertainties in long-term position calculations. The discovery rate of new asteroids continues to accelerate with improved telescopic surveys, revealing that the asteroid population contains far more objects than earlier estimates suggested. Each newly discovered asteroid adds another gravitational influence to the complex calculation required for precise orbital prediction, demonstrating that even comprehensive catalogues of solar system objects remain incomplete enough to affect the accuracy of long-term orbital forecasts. Asteroid collisions, occurring perhaps once per million years for kilometer-sized objects, create sudden changes in the mass distribution within the belt that affect the local gravitational environment. These collision events can fragment large asteroids into multiple smaller objects, creating new gravitational influences while removing others. The unpredictable timing and outcomes of such collisions introduce additional elements of uncertainty into long-term orbital calculations that extend beyond the purely gravitational perturbations of intact objects. The gravitational influence of asteroid belt objects on Earth's orbit operates primarily through their collective effect on Mars, whose orbit lies adjacent to the inner edge of the asteroid belt. Mars experiences more direct gravitational perturbations from belt objects than Earth, and these Martian orbital changes propagate through gravitational interactions to affect Earth's orbital evolution over extended time periods. This indirect coupling demonstrates how gravitational influences can propagate through the solar system in complex chains of cause and effect. Secular resonances, long-term gravitational interactions between asteroid orbital frequencies and planetary motion, create additional complications for orbital prediction by linking asteroid belt dynamics with planetary orbital evolution. These resonances operate over time scales of millions of years and can cause asteroids to experience large changes in orbital eccentricity or inclination that alter their gravitational influences on planetary motion. The chaotic nature of these resonance interactions makes their long-term evolution impossible to predict with perfect accuracy. Modern computational models of solar system dynamics must include the gravitational effects of hundreds of thousands of known asteroids to achieve the highest accuracy in orbital predictions. Yet even these comprehensive models remain incomplete due to the millions of smaller objects that remain undetected. Each additional asteroid included in calculations improves prediction accuracy in the short term, while revealing new sources of uncertainty that limit long-term predictability. The asteroid belt represents a microcosm of the challenges facing orbital prediction, a region where millions of individual gravitational influences combine to create collective effects that shape planetary motion over geological timescales. The complex interactions between asteroids, their resonances with planetary motion, and their own chaotic orbital evolution ensure that perfect prediction of their future gravitational influences remains impossible, contributing another layer of uncertainty to the already complex problem of forecasting Earth's orbital future. The rocky debris continues its ancient dance around the Sun, each fragment following gravitational laws with perfect precision, while participating in a collective motion too complex for complete prediction. The asteroid belt stands as a testament to the accumulated complexity that emerges when millions of gravitational influences combine across the vast timescales of planetary motion, creating patterns beautiful in their mathematical structure yet ultimately unpredictable in their detailed evolution.